This is Black Hole Evaporation by Nicholas Swicker and Elish Curran. Black holes are celestial bodies of infinite density that create a hole in the fabric of space-time. They are created from the gravitation collapse of the core of a star of at least 3 solar masses. Occasionally, the core of a star will fuse into a collection of neutrons, which can hold itself against gravity. But after a while, the neutrons will not be able to resist the force of gravity, and a black hole will form. This picture is a neutron star. Black holes are made up of a singularity event horizon and sometimes an accretion disk. The singularity is a single point of infinite density. The event horizon is the point at which the escape velocity of the singularity becomes faster than the speed of light, and the accretion disk is the matter in orbit around the black hole as it loses kinetic energy and falls into the black hole. Anything that is inside the event horizon cannot escape and will hit the singularity. Things that are outside of the event horizon will either escape the black hole or fall in. All black holes do not behave the same. Large black holes are cold and are known to radiate slowly, whereas small black holes are hot and should radiate explosively. An example of a black hole is Cygnus X1, which revolves around a blue supergiant. Cygnus X1 was formed from the collapse of a massive star and is referred to as a stellar mass black hole. Black holes are not the only abnormal things in space. There are also pairs of particles and antiparticles that come into existence and then disappear. These particles are known as virtual particles. A mathematical way of thinking of the spontaneous appearance of particles and antiparticles that annihilate each other is the Heisenberg uncertainty principle, in terms of energy and time. The particles pairs briefly borrow energy from the universe but give it back so quickly that in reality these virtual particles don't exist. Occasionally, however, before annihilation can occur, one of the particle pairs will fall into the black hole and the other will escape with stolen energy. This stolen energy is known as Hawking radiation. The radiation comes from the matter orbiting outside the event horizon and not from within the black hole. According to the law of thermodynamics, which states energy can neither be created nor destroyed, the black hole has to make up for the lost energy from the particle that escaped, and as a result it loses mass. The smaller the event horizon, the larger the curvature of space is, which therefore increases the rate of Hawking radiation. This is why, as mentioned before, small black holes radiate explosively. This radiation, now known as Hawking radiation, was discovered by Stephen Hawking. Stephen Hawking was born in Oxford, England on January 8, 1942. At age 21, he was diagnosed with ALS. The doctors predicted he would have 2.5 years to live. He revealed that before he was diagnosed with ALS, he was bored with his life, and there was not much worth doing. However, he then devoted his time to research, and one of the primary topics was black holes. Originally, physicists believed black holes didn't lose mass and were ever growing. However, Hawking proved that this was incorrect. In 1974, Nature published a paper by Hawking called Black Hole Explosions. Following this, in 1975, he published a paper on how black holes should leak mass and emit radiation. These papers covered that due to quantum mechanical effects, black holes can emit particles such as neutrinos and photons, which act like hot bodies with a temperature. Although these quantum effects might be small individually, over an extremely long period of time they can have a significant effect on the universe. Therefore, the thermal emission from these quantum effects can cause black holes to slowly lose mass and eventually disappear.
But first we'll need to know a little bit of quantum field theory. Don't worry, it's nothing too complex. The theory is this. Space is filled with these quantum fields, each one corresponding to an elementary particle like the electron or muon or photon. These fields can oscillate with different frequencies, much like the many different vibrational modes of a guitar string. These particles are just the oscillations of these fields, and like the oscillations of a guitar string, are comprised of many different vibrational modes. See the yellow oscillation in the second picture. These modes are still present in the absence of real particles. They fluctuate in energy due to quantum uncertainty, and this gives us what we think of as virtual particles. They are very different from guitar strings, however. They are very different in the fact that they can have both positive and negative frequencies. The latter can be thought of as a mode that travels backwards in time and corresponds to antimatter. When a quantum field is in a vacuum state, there is a balance between positive and negative frequency modes, meaning a balance in virtual particles, so they cancel out and no real particles exist. This is all fine in a flat space, but what if spacetime is curved? And indeed it is. Spatial curvature disturbs the balance of underlying quantum fields with the introduction of horizons, such as the event horizon of a black hole. Horizons cut off access to only certain modes of the fields. Hawking knew that black holes, with their insane spacetime curvature, would wreak havoc on nearby quantum fields. But in what way? To understand this entirely, he needed a full union of general relativity and quantum mechanics, a theory of quantum gravity, a theory of everything. It didn't exist then, and it still doesn't. Undeterred, Hawking came up with a solution. It goes something like this. He imagined a single space-time path called a null geodesic. It extends from far in the past to far in the future. This path passes through the location of a black hole in the instant before it forms. He then imagined a simple quantum field tracing this path, one that is in a perfect vacuum state before the black hole. See the oscillations, or virtual particles, canceling out on the left. The insane spacetime curvature of this black hole disturbs the fundamental vibrational modes that define the vacuum. By the time the fluctuations find their way back to flat space again, they look like real particles, as depicted on the right. A distant observer sees this as radiation coming from the black hole. This solution was brilliant. It allowed Hawking to compare the state of quantum fields where the nature of quantum field theory is well understood. To understand the close encounter with the black hole, he required an uneasy union of general relativity and quantum mechanics. In the absence of this, he used the Bogoliubov transformations. They can be used to approximate the effect that curved spacetime has on quantum fields. They describe a sort of mixing of the positive and negative frequency modes that are caused by that curved space. Hawking's calculations talk about scattering as one of the possible interpretations of these transformations. Certain modes of the quantum fields are scattered by the gravitational field of the black hole, depicted by the absence of the blue wave on the right, while the purple and yellow fields are left unscathed. With the loss of certain modes and not others, the vacuum must be constructed from the remaining ones. This distorted vacuum looks like it's full of particles. The absence of the lost modes tells us what Hawking radiation should look like. Black holes tend to scatter modes with wavelengths similar to their own sizes. The quantum field this produces is disturbed in the same wavelength range and so produces particles with the wavelength as large as the event horizon, or the Schwarzschild radius. Hawking calculated the frequency distribution of the radiation and found that it should look identical to thermal radiation, as shown here. Black holes have an apparent temperature that depends on mass and is proportional to the surface area of the event horizon. This is the Hawking temperature, as shown. Okay, so we followed Hawking's narrative. Now, what about the whole particle-antiparticle pairs being ripped apart by the event horizon? Hawking's math describes the splitting or mixing of these positive and negative frequency modes by the black hole. It's fair to interpret the mixing of these modes as the upgrade of virtual particles into reality, and for the escaping modes, there exists a corresponding set of frequency modes that are bound by quantum entanglement that are trapped inside the event horizon. Those can be thought of as a swallowed antimatter partner, so the splitting of matter and antimatter part of the basic picture is reasonable. Some aspects of this, however, just don't work. Firstly, this Hawking radiation isn't localized. In the basic picture, there appears to be specific points on the black hole where the radiation is flowing out from. Remember the radiation has a wavelength the same radius as the event horizon? That's its de Broglie wavelength. There is a massive quantum uncertainty as to where the radiation comes from, so we can't define it to be at specific points on the surface of the event horizon. Instead, it must come from the global black hole, or the black hole as a whole. In fact, an observer passing through the horizon actually sees nothing, no radiation. To them, space is locally flat. This radiation is visible only to distant observers, except when you turn on your hyperjetpack and hover right above the event horizon. Then you do see radiation. You see Unruh radiation, but that's a whole different topic on its own. We followed Hawking's narrative of why Hawking radiation exists, but this is actually only one of the possibilities outlined in papers by physicists. In fact, in 2001, Parikh and Wilczek got the same thermal spectrum by thinking about particles escaping from under the event horizon through quantum tunneling. The common thread here is the quantum uncertainty. And as brilliant as all of these workarounds are, there's still just that, mathematical hacks attempting to describe something that cannot be truly known without a theory of quantum gravity. And until one emerges, the true nature of Hawking radiation will remain mysterious.
Following this, the implications of Hawking radiation can be pretty huge. Some other attempts at describing black hole evaporation say that the loss of mass of a black hole is due to quantum tunneling of elementary particles from within the event horizon. This is a pretty big topic to be covered all on its own. Another quite obvious implication is that black holes actually emit energy, which previously was unknown and was thought to be nonsense. The final and certainly most interesting implication of Hawking radiation is the black hole information paradox. A fundamental law of quantum mechanics is that quantum information can never be destroyed. That is, information should never be lost to the universe. The fact that a black hole can consume matter, and then after a time evaporate, leaving nothing left, clearly violates this fundamental rule. There are theories that try to remedy this paradox, but those are for another presentation, or video.